Okay, this is so we started chapter 4 last time. We quickly reviewed those sections and we'll try to finalize this strong ground motion. So we have seen section 4.1, strong ground motion measurement instrument is seismograph or accelerometer. And we have seen the design concept behind. All are represented as a single degree of freedom system with a stiffness and a mass. And from our general equation of motion, we have those solutions for dimensionless, non-dimensional forms of the solutions, which helped us in the design of this displacement measuring instrument, such as the drum, and which has also a drawback because we may need a very large mass and large size because the seismic motion can reach to 2 feet, 3 feet. And on the other hand, we had accelerometers, which are small in size and very popular, which picks up accelerations. And you can have various types of these measuring instruments. And section 4.2, we have seen the strong ground motion instrument arrays worldwide. This is just an example. You can have a wide variety of measuring instruments all over the world. And a strong ground motion data, the raw data, the raw data can have some noise or unwanted frequencies, and but you can get raw data from several sources online these days within minutes from the occurrence of the earthquake. USGS is one site, University of Washington is another site, and many others. There are many sites that international sites you can find raw data. But once you find raw data, it may contain error, either a background noise, construction around and things like that, or even instrument error. So the raw data by itself is not usable. You'll find some fun stuff like non-zero initial values. When the earthquake starts, doesn't start at peak value, it should start from 0. And when it's finished, it should be around 0 for accelerations. You may have a little bit of displacement, but acceleration velocity should start from 0 and finish at 0. So we need to process this. And if you don't process it, just to plot acceleration and integrate to velocity, integrate to displacement, you may see some drift in the raw data. To avoid this drift, we need to filter out the frequencies which cause it. So there are different softwares to do this, to process raw acceleration data, because the most popular of recording is acceleration, and you may not see the error with the acceleration data, but if you plot the velocity and the displacement, you can clearly see the drifts because of the error. You can see this corrected and uncorrected input motion or acceleration records and velocity record. You have the dark line, which is shifting from the blue line, and also for displacements much clearer. The red one is the corrected one, and this dark one, dash one, is uncorrected one. So that's why we need to correct it. And correcting commonly it is done by filtering out unwanted frequencies. For civil application, usually the frequencies of interest are anywhere from 0.1 to 25 hertz most commonly. But we can go higher, 33 hertz or 50 hertz or 100 hertz even sometimes, depending on the criticality of the structure. But the more you go, the more you try higher frequencies, the more expensive is the solution also, because the modeling, like a finite element modeling or things like that, it will require very fine mesh to capture higher frequencies. So that fine mesh requirement, it makes the model really large for the solution. It may take lots of time for the solution. So the smaller the frequency, the faster the solution. We'll see that in detail when we go to the applications. If you are trying to capture higher frequencies, the meshing requirement is very high. So there are different kind of filters to do this. And this is not usually done by hand. There are free softwares available to do this. And my recommendation for you is the Seismo signal from this website, from Seismosoft. It's a European company, I think in Netherlands or Sweden. I forgot what they are, where they are based. They provide a 1 month free software to process input motion. You can download this and use it to do your homework, to do your mini project. And others are a little bit complicated. You can use also MATLAB, but it may not be as friendly as a Seismo signal software. And we also start the ground motion parameters. When you have a record acceleration time history, there are 3 parameters we are most interested, or which can fully describe it. The peak value, which we call amplitude, or the significant duration, how long the significant peaks are there, and also the frequency content. Frequency content is a big concept. We'll see it in detail. So amplitude parameters is just the peak acceleration, PGA, and for velocities, the peak velocity. You can go through the rest of the write-up. Same is true for displacement. And drawback of using amplitude parameter alone. So when we apply it, we want to fully describe all motion. If you try to choose an input motion just based on the peak value, that may not be the most conservative acceleration, because a peak value is just, it can be one spike. Let's say this is 1G compared to 0.7 G right here, but the energy content, the duration is very small. You have a larger duration with several peaks. This one has more energy and it's going to be more damaging to our structures. So the way you choose input motion, it shouldn't be based on peak value. You need to consider duration. You need to consider energy content. You need to consider the frequency content. For frequency content parameters, what we meant is how spread the frequencies are. We have, I mean, if you go to a city and try to see the buildings, you have a wide variety of buildings with different periods, with different fundamental periods. And when we talk about frequency and period, they're the same thing. One is a reciprocal of the other. So the larger spread you have, the larger possibility that it can damage more structures. If you have a very narrow frequency input motion, it can damage only buildings within this area. So it's not that, it doesn't have that much large frequency content, and you may miss out. You may design your structure for this red one, and you can even use a peak value much larger, but your design is only with this frequency. If you have a structure in this area, let me go to my pen. If you have a structure in this area, it's now not dominating. So the blue one, which is a lower amplitude but over a broad range of frequency, has a much larger acceleration for design. So frequency contains a larger spread. It shouldn't be like a narrow range, or it shouldn't be like a single frequency. Usually our structures have multiple frequency, different modes of shape, but some components, electrical, mechanical components, they may have single frequencies. And that's not the one we're talking. We're trying to get a spread of frequencies. When we say, low frequency, high frequency, or a range of frequency, this is what we meant. So we stopped last time over here. And now, if you have acceleration time history, there are 2 ways to convert it into a frequency motion, because we're talking in terms of period and frequency. We know the period and the frequency of our structures. We want to understand the input motion similarly. So if we want to convert our motion into a frequency domain, the first one is frequency spectrum. Frequency spectrum, what it does is, it's assuming the time history. Let's say this is acceleration time history. The irregular, the most complex one you have. What it assumes is the Fourier spectrum considers the irregular or the non-periodic. It looks non-periodic when you see it. But what Fourier spectrum assumes is it's a combination of several periodic motions, many thousands. So the irregular motion is a sum of several regular motions. That's what Fourier spectrum is considering. So you can, it may be thousands and millions of these small or these various periodic motions to give you the one which is irregular motion. It's like the mode shapes we talked, the irregular deformation in a structure. It's the sum of several modes. We have seen that in chapter 2. That's the main concept. So A is the Fourier amplitude, and omega is circular frequency of the sine wave. In this case, we're using several sine waves, several periodic motion, and phi is the phase shift in each of them. So what it means practically is, let's say you have one motion with one wave has a frequency of, say, omega 1. If you have one periodic motion, let's say this is acceleration, this is time, then that has, give me 1 second. Sorry on that break. So if you have a wave, let's say acceleration time history, which is periodic, then we know the period, we know the frequency of this, or we know the circular frequency of this. Let's say it's omega 1, right? And in the phase is Fourier amplitude spectrum. We are talking the Fourier spectrum. Phase is Fourier amplitude spectrum. In the Fourier amplitude spectrum, all this motion is represented by a single point, which is omega 1. This is acceleration time. Now we are representing it into phase, amplitude versus frequency. That's how you get the frequency domain plots. So you have acceleration time history. This periodic motion has a single omega 1. Then we put a single omega 1. Let's say we have another one with a wave which has omega 2 frequency or circular. Omega 2 is 2 pi f, 2 by period. So this has omega 2. In the fast plot, it's just a single point, omega 2. Now let's say, now you have omega 1 on omega 2 combined. It looks a little bit irregular, right? But all we did is just combining the two acceleration time history motion. So this now, omega 1, omega 2, you have two frequencies. So in the fast, there are just 2 points. It goes on the same way. If you have several irregular motions, if you have several hundreds or 200s of omegas, now you'll have 200 points. And finally, you join them, all of them. When you join all those, now you'll get a Fourier amplitude spectrum. So you converted your motion from a time history into a frequency domain. Once you get it in frequency, if you put it 1 over period, or you can simply get it in terms of period or fundamental period. We'll talk about the fundamental period, but frequency and period, they go with each other. You can convert it easily. So that's how you convert. That's the concept to convert a time history motion into a frequency domain, at least in this case for Fourier amplitude spectrum. So this is not going to be done by hand, because it's, imagine you have several irregular motions here. This is a combination. We're saying what Fourier spectrum saying is this acceleration time history, this is the one we get from recording stations. We get the raw data, we process it. Let's say we have corrected now, but this is the motion. But this is acceleration time. But we want to see it in Fourier spectrum. You can convert it into Fourier spectrum like this. And this is just an example. You can use softwares and you can convert it into Fourier spectrum. So here now you have it in frequency domain. This is in time domain. Now the difference is in time domain, there are various advantages we get. In time domain, let's say you get the peak value of the acceleration. In frequency domain, you get what frequencies are sensitive. This input motion has a peak value, let's say around here. So structures, let's say this is 2.5 hertz. A structure, the frequency range of 2.5 hertz, they are going to be damaged a lot, or they are going to receive significant force from that earthquake, compared to structures outside this frequency range. If you have a structure in the 25 hertz, it's not going to feel much. Or if you have a structure very close to the zero, very lower frequency, it's not going to feel much compared to the 2.5 hertz. And the frequency, it tells us, for example, if you design your building, Mexico City, we have seen tall buildings and shorter buildings damaged, various ways. The shorter buildings are around 5 to 15 stories, they get damaged a lot because the motion which came, that point, it has peaker values in that range and resonance occurred. But taller buildings, which are more flexible, they didn't get damaged. They have long periods or short frequency, they are in this range. They didn't get damaged. So that's the advantage of this Fourier amplitude. It tells us the frequency content. And this frequency content has direct application for our modeling. When you do SSI, we can say, okay, what frequency we're capturing. It will tell us the mesh size, especially in the soil stratification. In some cases, you may say, oh, the peak frequencies are around 2.5 hertz. So because if you have a limitation in your software, you may want to include, well, I would like to include only up to 10 hertz. It's not bad, up to 10 hertz, but still you're capturing the peak values. But if you have advanced software, you can go to 25 hertz, even beyond. But when you go, to higher frequencies, you see it getting lower. And some other input motions, you may have something like this. It's not bad in the lower frequency, below 5 hertz, but it gets bad from, let's say, 10 to 20 hertz, then it gets lower. So depending on your frequency content, your structure can be designed. So you can choose also the cutoff frequency. This cutoff frequency is very important parameter in SSI, soil structure interaction analysis. This cutoff frequency is the one directly telling you, okay, what frequency you're capturing. This may come from regulation or a design code. You may be asked to capture up to, let's say, 25 hertz or 33 hertz. And this determines your mesh size. When you model, let's say you have a structure, let's say you are doing SSI, and now you have a soil mesh. Your soil, even if it's homogeneous, you need to have some layers in the model so that the wave propagates properly. And for that, the thickness of each layer, that's the finite element size. The thickness of each layer is determined from the cutoff frequency. The thickness of each layer, you'll see it later. It's going to be determined by T is equal to the shear wave velocity by 4 times the cutoff frequency. And sometimes this parameter can be 5. So you'll find it, for example, Flux 3D has this formula. This is telling you, okay, the thickness should not be more than this. If it's more than this, the wave is not propagating. And now see it, to determine this thickness, shear wave velocity, it's a soil property. FC is that cutoff frequency. And that cutoff frequency, you're getting it from the Fourier spectrum. You can look at it and say, depending on your model size, you can say, okay, I can go up to 5 hertz, 10 hertz. If you have a limitation, you can only do very little. Let's say 5 hertz. You can go up to 10 or 20. But the larger cutoff frequency you go, let's say if you put 25 here, the thickness is going to be much smaller, really fine. And if you have so many finite elements, so many mesh size like this, and this is vertical, the same is true. You can keep aspect ratio of 1. You can do the same horizontal in the plan dimension. So the number of finite elements increase as you increase the cutoff frequency. So the solution is going to take a lot of time, or you need advanced, machines to do that. So that's the advantage. When you do SSI, you're going to do this. Determine your cutoff frequency to determine the thickness of your soil layers, or the mesh in the soil layer for your model. That's one application. So Fourier spectrum, just to give you an example for previous earthquake, this is the 1989 Loma Prieta earthquake. And if you plot in a rock site, this record was in a rock site. This one was in soil site, which means it's like you have the ground, you have, let's say, bedrock, you have one recording at the bedrock, you have another one somewhere in the soil, or even at the top of the ground. So this is just telling us, if you see here, rock has higher amplitude at low periods. For rock, the peak values were occurring around 0.5 second. And for soil, the peak values are happening around 1.5. This is tell us that soil has larger period compared to the rock. That's a general observation. That's how it is. Soil is more flexible and it has high period compared to rock. In rock, you can see the lower values at low period, 0.5 compared to 1.5. Drawback of Fourier spectrum. You can get a Fourier spectrum, but it's not that much helpful. That's not what engineers want. It tells us to determine the cutoff frequency, but it doesn't go beyond that. Tell us the amplitude, the frequency, but there is another spectrum, which is called the ground motion response spectra. This has much application, and we're going to focus on that one. So that ground motion response spectra, what it is, let's say you have a time history. If you have a time history, and let's say you have 1 degree of freedom system with a spring and damper. And we know this because this is a single degree of freedom system. We know the fundamental period. We know the fundamental frequency, square root of k by m. Now, if you apply this time history, acceleration time history, this is in time domain. We're trying to convert it into a frequency domain. If you apply this acceleration time to this motion, we can get the peak value. And say we applied it here, get the peak value of that response. Let's say it's this point. And let's say we have another 1 degree of freedom system with different period. This is, let's say, T2, this is T1, this is T3, T4, T5. And apply the same input motion, get the peak value of the response. Let's say in this case, the acceleration. For the third one, we have different fundamental period, get the peak value. Apply this input motion, get the peak value. Now connect all the peak values. We're trying to relate the response of this input motion, the response of our structure to this input motion. If you see it in the Fourier spectrum, we were not talking about our structures. That was purely changing into a frequency domain. But now we are relating it to our structures, and we're considering various kinds of structures with different frequencies or different periods, because we have a range of frequencies for short buildings and tall buildings. That's what we're trying to capture. The tall buildings have long period. They are around the end here in this plot. The shorter buildings are stiffer. They have short period. They are on the left side of the spectrum. Now what we do is forget about the time history response, but pick only the larger values, the peak values. If you do that, now you get response spectrum. It's a response of the structures for the seismic motion. So you can do this. I mean, you can do this with softwares pretty easy. There are software doing this in few minutes. But the concept is like this. Now you have a response or the time history motion represented with a response of the structure. So if somebody give you a structure around here, let's say it has a period of between these two, then you can go in there and you can estimate the peak value. And you can say, hey, this is the acceleration, the peak acceleration, which will act on that structure, and you can use that peak value. If somebody give you like a very tall building somewhere here, you can compute that period. With the period, you can go to that spectrum and get that acceleration and use that acceleration for design. So this is also in frequency domain, but related to our structures. That's why this is a much better application for civil engineers than the Fourier spectrum. Is that clear? And usually this is developed, you'll see it in as input in your design codes, and you may ask to develop this. Usually it's common to develop this for 5% damping. The damping that you use for each degree of freedom is developed for 5%, but it's also developed for other damping values. For 5%, it may be like this. Then for 2%, then if it's larger damping, it gets lower value. It's maybe 10%, 5%, 2%, like that. So you have a series of charts like that. So example of response spectrum plot is, for example, the 1940 El Centro earthquake. This is acceleration, time history. You can use software to convert into a response spectrum, or it's also called, that have different names. It can be called pseudo acceleration or spectral acceleration. So, but this is with period, and you can easily get it with frequency. It's just 1 over period is frequency. So the chart would be in the other side. If it's frequency, you'll find it changes the peak value just changes because of where the period or whether it is frequency, but it shouldn't confuse you. And this is the other direction motion in the north-south direction. You can convert it, but the peak values for this, you can see it, it's within 0 and 1 second period. And the vertical direction, you can convert it and see. If you pick like if a period of 1 second or 2 seconds, you can pick all the values. For 2 seconds, you have 0.2 G in this case. And for the north-south direction, you have around a little bit less than 0.2. And for the vertical, it's really small, maybe 0.5. So if you get the fundamental period of your structure, you can get the corresponding acceleration and use it for design purpose, like in the static case. If it's in the dynamic case, let's say if you're using a SAP 2000 or a STAR Pro analysis, this is your direct input. They call it also actually response spectrum analysis. Response spectrum analysis, there is a time history analysis where you give the time history input itself, or there is response spectrum analysis where you provide the response spectrum. Now, the time history is usually very costly. It takes a lot of time because it's at a very small delta it's doing it. In the response spectrum, it's very fast because what the software does is it quickly determines where your period of that structure in and picks up the corresponding acceleration. That's it. Applies it at all the masses or the finite elements corresponding to that. But the time history, it goes by time. Let's say if you are using a delta T of like 0.0001, then this takes a lot of time to solve it. So people choose a response spectrum analysis. It gives you a fast solution compared to a time history solution. So this is a direct, you will see, those of you who will be doing a software analysis, you will be using this. Either you'll be doing time history, very time taking, or response spectrum, where your input is a response spectrum. Predominant period. Predominant period is like what we call the fundamental period. It's the period at which the max spectral acceleration occurs in a response spectrum. It's like if you have a response spectrum like this, well, in this case, it's smoother. The peak value where it is happening, that's the predominant period. If you have input motion or response spectrum like this, you don't want to have your structure to have a period somewhere close to this. Or if you have it within this range, it's going to receive the peak value. That's what we saw resonance, if you noticed. We don't want our structure to be in the range of the peak values. We try to stay away from the peak values. It's not that smooth usually. You'll have it much sharper than my plot here. The peak value can be here. This is a predominant period is what we define this one. And you want to stay away from the peak value range. Or you want to design your structure somewhere here or somewhere here. And if you do it here, make sure you have, you introduce some damping, you design it well, the reinforcement and everything, it's going to be costly. Because you want to avoid cracks. So for this response spectrum, we looked at in terms of acceleration, but it can be represented by velocity and displacement. It's a linear plot. They have a linear relationship. Velocity is, related with displacement with 2 pi over period, or acceleration is also related to the displacement, 2 pi by period squared by d. So if you get the acceleration period plot, you can easily get the velocity and the displacement plots. So like this. You can have, let's say, if you get it with acceleration period plot, response spectrum, then getting the velocity and displacement is just, you can apply these equations. Or the software will give you directly a velocity spectrum or a displacement spectrum. But the most common I have been using for design is the acceleration plot. And this, now, when you have a response spectrum, the big advantage is it gives you a quicker solution in the softwares. It's also advantageous for a static solution. Because if I know the fundamental period of my structure, I go in there, let's say I have a period of 0.5, then the corresponding value is 1.09. So then this is the acceleration you'd be using for design. This is not, there are other factors to include, some amplification, some conservatism. You're not only going to use the peak value. And sometimes when you use the peak value, it may not be feasible. You may have failure. But conservatively, you can use peak value amplified with certain value, like we call it multimode factor, like a 1.5, and use this for design, for static design. I'll show you example how you can use, like with a hand calculation, acceleration obtained from a response spectrum. Let's see now the difference or the parameters, how we relate between a time history and a response spectrum plot. Let's say acceleration time history. This is acceleration versus time. And this is what we get from recording stations. And let's say, in this case, this is a row. You can see it that the initial value is not 0, the final value is not 0. So this needs to be corrected. Let's say you smooth it, you filter the unwanted frequencies, and you plot it. Or directly for this raw data, you can get the response spectrum plot. This is the corresponding response spectrum. This is in time domain. This is in frequency domain or in periods. Now you know the difference between both time and period have the same unit. So don't get tricked. This is like a period. Omega or 2 pi. Omega is 2 pi f, right? So that's in terms of vibration. This is just time. Here you have your single degree of freedom system. Here is just a time. So now the peak values, if you see here, if you have a peak value in time history plot, let's say around here, maybe around 0.35 G. It doesn't matter whether it is negative or positive, because when it's time history, it's just oscillating. You can take the absolute value. That peak value in the response spectrum plot, it's corresponding to the 0 period. Why? Because the 0 period, because this usually the peak values, they occur at high frequency. It's a spike in high frequency. Or high frequency means it's very low period or very rigid. This is a ground motion recorder. The ground moves rigidly. And the ground has very high frequency or extremely low period. That's why you have this low period related to the peak. It doesn't matter where the peak is. The peak can happen somewhere here. But still, that peak value is always corresponding to very low period or the 0 period in terms of the acceleration, the response spectrum plot. So as soon as you see, if somebody give you this, which means the response spectrum, don't think that the peak value in the response spectrum is the same as the peak value in the acceleration time history. Because the response spectrum, it's giving you the peak values for different, stiffness and damping, or different periods of that single degree of freedom system. And if you are consider the peak value, this is the ground peak value. The ground is very rigid. So the ground peak value occurs at 0 period. So that's what this slide is telling you. And because we have a relation of spectral displacement, velocity, and acceleration, we can actually put them together. And we can have a single chart. Usually we call it tripartite plot, where you have all of them together. You have a period on the horizontal axis and spectral velocity in the vertical axis, and the spectral acceleration, this diagonal, and spectral displacement, the other diagonal. You can have this, for example, damping ratio of 2%, you can have this plot. So the way you get your acceleration or velocity or displacement, your first input is period. Let's say you know the period of your structure. Let's say you have a 10-story building and the fundamental period, let's say, is around 1 second. If that's the case, what you do is take 1 second and go vertically to the chart. Or in this case, let's use this, the 2 seconds, it's already done here. With 2 seconds, you go to the chart directly. And the values for velocity, spectral velocity, go from this point perpendicular to the velocity plot. In this case, it's 23.5 inch per second. If you're interested in the spectral acceleration, which is the most common, go from this point on the chart perpendicular to this diagonal. So in this case, if it's going to be like this. So the acceleration, spectral acceleration, is 0.1 G, 0.191 G. And for the max displacement or spectral displacement, it's going to be around here, which is 7.47 inch. So this, you'll find it in code books. Sometimes they provide it individually, acceleration, spectral velocity, spectral displacement, and most commonly you will see it all together in tripartite plot. So just start from your period, from the period go to the chart, then go perpendicular to those axes and get your value. This is the beauty, because acceleration, displacement, velocity, they have a linear relationship. This is how you can put it together for design purpose. Now, here we saw it only for one damping value, 2%. You can have it for multiple damping. The same chart, but multiple damping. In our, commonly we see plots from 0.5% to 20% for civil structures. and the lower damping, the higher values, and the higher damping, the lower values. So you can have that single degree of freedom system, the mass, with different damper. That's what it means. Do the same thing, but different values of damping. If you do that, you have this series of charts. The way you get value is the same. Let's say for our 2%, let's assume, in our most common cases, let's 5%. For 5% damping, let's say we have a structure with period of, let's say, 2 seconds, right? And damping ratio of 5%. If you're given this, and if you are asked to find the design acceleration, then let's say 2 seconds, you go up vertically up to 5% plot. The 5% is the maximum in this case is 20%. Then we have 10%. Then we have 5%. So our chart is the third one from the bottom, or the third one from the top also. You go vertically up, which is this value. Now, once you are in the chart for 5%, you can go for acceleration, go perpendicular to the acceleration plot. So the corresponding pseudo acceleration or spectral acceleration is around, this is in log chart. So this is 0.1, 0.2. So it's 0.2 g. The design acceleration is 0.2 g. You can do the same thing for velocity or displacement. So make sure you are in the chart of the required damping value, and make sure you go perpendicular to get the values. So the pseudo deformation or spectral displacement spectrum plot, it gives us the peak deformations. The pseudo velocity, it gives us the maximum peak strain energy. It's like a kinetic energy. And the pseudo or spectral acceleration, it gives forces, the inertial force, the mass times acceleration. Usually this is the one we use because we are interested in the force caused by the earthquake on the structures. And once we get the force, we can get our bending moments, shear forces, and everything. For our application, we mostly use this part. We use acceleration. That's the reason we use acceleration. Once you get acceleration, then you know your mass. So mass times acceleration is the force. Let me show you a quick example using a response spectrum plotters. Let's say we have this, the water tank structure shown below has 1,500 kilogram mass at the top right here. And the support cantilever beam has elastic modulus of 30 megapascal. And section modulus of inertia of I10 meter raised 4. Assuming the weight of the column is negligible, for now, assume this is negligible weight. What is the seismic bending moment at the foundation level using the El Centro earthquake response spectrum in the previous page? Consider 5% damping. This is just to show you how you can use those plotters. And this is for a quick hand calculation. You don't need even here in a fancy software, anything. For a quick hand calculation, you can use this. You know the mass, you know the elastic modulus, inertia, and you know the height. I think the height, it's supposed to be, L says 25. I don't know how much I used here. Should be, let's say, this is 20. Check it which one I used here. I use MathCard to calculate this, and it doesn't show me how much I used, but it should be identical. This L is supposed to be this. Should be H. Or this L is H. So correct it. I'll correct it for next time and correct it, and I'll send you back. So now, this is how you get it. We need the period, right? What's the period of this structure? This structure, if you see it, it can be simplified as a cantilever beam. It's a cantilever beam with a mass at the end. And we're making assumption to ignore the mass of the beam, because this mass is significantly larger. So you can use, there is a Roark's formula book to find the period or the fundamental period of this cantilever beam with a mass at the end. This is a free book. You should have it. I think I sent it last time. It should be in BiT if you don't have it, but you can download it also. It's a free PDF. If you use Roark's formula, they have different formulas for different structures, different configuration of the loading. In this case, we're using this section. Or if you use table 16.1, uniform beam, left end fixed, right end free. Right end with W, mass. Beam weight negligible. So we are ignoring the weight. If you assume this, they have a frequency, a fundamental frequency of that structure, or in this case, the cantilever beam is given by this. Elastic modulus, moment of inertia, the mass, and L is the H we put here. If you do that, it gives you the fundamental frequency of the structure is 0.99 hertz. It's like the period is 1 second. Period is 1 over frequency. Now, here is the trick. Once you get the period, you can get the acceleration. Go to the L center or the quick plot we talked earlier, right here. With 1 second, get your value for 5% damping. Somewhere here, and I may not be correct. So get the acceleration around here. The acceleration is around 0.5 g. If you see it here, I may not be correctly doing it. 0.1, 2, 3, 4, 5. This one. I missed it a little bit in the plot. So that's how you get your acceleration. Once you get your acceleration, which is 0.5 g from L center earthquake for a period of 1 second. Now, for conservative, usually we apply 1.5 factor for multi-mode factor, because we're using a fundamental period, but structures normally have multiple modes. When you see response spectrum for structure, it's not only one mode. You may see something like this. You have first mode, second mode, third mode, fourth mode, like that. Usually the first mode, what we call the fundamental period, the fundamental mode, that's very dominating. But to account for other modes, in a complex structure, you may have several thousands of modes. To account for the other modes, we increase the acceleration by 50% in the static analysis. If you're doing like a software, like a SAP 2000, Start Pro analysis, they automatically compute the other modes. They don't conservatively increase by 50%. They automatically get the other modes and use the modes. But in our case, for a hand calculation, it's observed that if you do several simulations with, let's say SAP 2000, and do by hand, it's observed the increase is around 33%. There are papers doing that, published papers. But conservatively, we are increasing it by 50%. So this 1.5 factor, it's common, and it's called a multi-mode factor. Now you have your acceleration, you have your mass, then what's the moment? The moment is, the force is right here, right? The force we get is right here. That force is acting on the mass at the top. We know the height. We know that this mass. Force times mass, acceleration times mass is the force. So this you see here, that SA, spectral acceleration, times the mass, it's our force. Force times L, which is this height, equals to this. I think I'm using L of 25. Because in MathCAD, this has to be corrected to 25. Because in MathCAD, when I do this, L goes with the symbol. L is 25. If you put L directly, it uses what's defined here. So we're using L25. So the moment at the base, about x-axis, let's say we get it this much, 275,000, or 275.8 kilonewton meter. You can do the same thing on the other side, about y-axis. So you'll have biaxial moment. Let's assume that you get, the response spectrum in the other direction also the same, giving you the same spectral acceleration. So you can assume the moment about y, the moment about x, they are the same values. So you get your biaxial moments. So this is just to show you how the response spectrum plots can help you to get the reaction forces at the base. Once you have, the moments, you have your vertical force. You can use also the vertical acceleration to get the vertical force. And on these dynamic forces, these biaxial moments and vertical force, seismic acceleration, they are dynamic. They are from seismic. You will add also the static load, especially together with the vertical. So you have a vertical force and biaxial moments acting, and also shear. Because whatever shear force you have here, it comes as a shear down at a base shear here. This is a simplified way, but there is also a way to find it a distributed base shear. At any point you can get it, but the maximum shear you can simplify it like this. So this helps you, like with a simple hand calculation, you can do a seismic static analysis, or it's called pseudo-static analysis. And those response spectrum plots help you to do this. And the second example, it's the same. It's trying to use those response spectrum plots, but now let's assume it's a motor generator. A new generator motor is to be installed on a concrete foundation floor using 4 anchor bolts. These are the anchor bolts at the bottom. The motor has a weight of 1,000 kilograms with a CG of 0.5 above the foundation floor. Assuming 5% damping, a central earthquake response spectrum, which is that plot we have seen, in both x and y direction, what are the maximum shear force and bending moments at the top of the foundation floor, or the CG of the bolts. Design the minimum anchor bolt size to resist the seismic forces. This is the same thing. You know the mass, you know the height of the CG, and now the trick is, it may not be easy to find the period of this motor, but usually they give you from the manufacturer. If you attach it, then motors, rigidly attached motors, they have higher frequencies. The manufacturer can provide you. It may say 60 hertz, 70 hertz, or sometimes it may be missing. You may not have it. If you don't, let's say in this case, you don't have it. If you don't have it, what you can do is you can do the peak spectral acceleration. No matter what frequency it is, let's say this is 5%, right? If you go to the 5%, this is the chart we're talking. If you don't know the period, let's say it can be 0.05, it can be 1, it can be 20, right? What you can do is do a conservative analysis. Just pick the peak value, peak acceleration value from the plot. The peak acceleration value, this is the acceleration line, right? The peak value is, let's say, this is somewhere here. Am I in the correct one? Yeah. It's around between 0.9 and 1. Somewhere here. So if you use the peak value, it doesn't matter. You're bounding all the other values. So if you don't know the period, you can use the peak value conservatively. That's what this example is for. Let's say peak spectral value is 0.9 G. Assuming we don't know our fundamental period. Use your multimode factor and do the same math. And you can get the forces These are the forces. And now you can get the moments because you know height from the floor, the CG. So you have the forces at the CG in both directions, and now get the moment here, mx, my. So once you get the forces, it's easy after that. It's like a static calculation. The difference is now getting the accelerations to do a simplified static analysis. This is very conservative in design. It's quicker. We usually use it just for a quick check, but it's so conservative, it's penalizing. For example, when you design your bolts here now, you need larger bolts. But if you do response spectrum or time history, you get more realistic. Time history takes a lot of time, but the advantage is the solution is more realistic. If you do response spectrum, it's much better than the static analysis, pseudo-static analysis. So you have, right now, you're looking at 3 analyses. You have a static, a simplified analysis like this, using a single acceleration value from response spectrum. That's called pseudo-static analysis. Or the second one is you can do response spectrum analysis. You can put the response spectrum plot for SAP or StatPro, and they will analyze it. It will analyze it. And the third one is you can use your time history. It's very time-taking, but more realistic. So as you go down, it's more time-taking, more expensive, but more realistic solution. As you go up, it's a very quick solution, but it's expensive. Expensive in the sense that the bolt sizes you need here would be much larger because the forces you are getting here, they are much larger. They are conservatively larger on purpose. So these are the 3 solutions you can do. So once you get your force, your moment, you can design your bolts, anchor bolts. The maximum tension force on the anchor bolt, you can get it. Tension force at each anchor bolt by taking moment equilibrium. Once you get your tension force, then you can use design charts to pick what kind of bolt I should use. For example, in this case, considering the 3/8-inch diameter Hilt-Quick bolt 3. This is from different manufacturers. Depending on what manufacturer, what kind of bolt you are using, they provide you the allowables. You can go to their design manuals and pick the right value. If you pick, for example, for this case, 3/8-inch diameter Hilt-Quick bolt 3, expansion anchor, concrete anchor with 3000 psi, then the allowable values are this much. Then you're comparing, okay, the tension I have is 1.6, right? Kilonewton, 1.6 kilonewton. And the allowable is much larger. So you're okay. Do the same for shear. The shear is 11.6 kilonewton. We found it somewhere here. Oh, well, so 11.6 is the allowable. It's in the next page. This is from the manufacturer, vendor manual. Let's say in this case, we're using 3/8-inch bolt, and we're trying to get the tension and shear allowables. And the kilonewtons are the lower value, and we're talking the 3000 psi concrete. So these are the values where the allowable values, 11.6 and 10.7. And this is that quick bolt 3. Usually you can drill and insert it, then torque it to achieve, and it expands. It works by expansion. You see the design here is you drill a hole, you insert the entire thing, and when you torque it finally, this thing expands. That's why they call it expansion anchor. So these are the allowable values from there. Compare your allowable value to the design forces. It's much larger, so you're okay. And for designing bolts, there is some other parameter you should consider. Interaction, the shear tension interaction. The tension force by the allowable plus the shear force by the shear allowable, it should be less than 1. That's a code requirement. In this case, we get 0.44. We should be less than 1. We're good. So this is just a design example to show you what you can do by hand. A simplified, this is the most simplified seismic analysis you can do. If you want some more complicated, then go for response spectrum. But you'll require to model the structure and use some software. And that same model you prepare, you can apply time history, but it's going to be time taking. So the first one, it may take you half a day to do it or a couple of hours. The second one, maybe 2-3 days, depending on the structure. The third one, maybe a week. So it gets more expensive with time, or it gets more time taking. The more fancy, the more accurate you are, it takes more time. Duration parameter. The duration, we discussed it briefly last time. You may have seismic input motion with a larger peak, but shorter duration. But another earthquake is a lower peak with a larger duration. So depending on which one you choose, it's about duration is another parameter you should consider. So it's not only that we considered in the previous design. If you see it, we were picking only one single acceleration. We were not considering, duration. To account for all that, what we used is we increased this 50% by calling it, multimode factor. But duration, there is a way to consider duration. Duration, we can estimate duration in two ways. We call it bracketed duration. If you have a time history acceleration motion, then the duration is defined as, if you make a range, the first peak which reaches to 0.05 G, and the last peak to reach 0.05 G, you can make these bracket lines, the top and the bottom lines. The bottom one is negative 0.05 G, top one is 0.05 G. So this is what makes it bracket. So if you have a motion which touches, the first time it touches 0.05 G, and the last point it touches 0.05 G, then the bracket duration define it. That's the duration of the significant duration of the input motion. In this case, it can be around 2 seconds. There is another one for duration. It's called areas intensity. Areas intensity is if you integrate the acceleration times 3 from 0 to its time, then the energy content where you get from 5% to 95% is the duration. It's better clear on the next slide right here. You have acceleration time history, and you can use softwares to do the areas intensity. If you do the areas intensity or integrate that acceleration, and where you get from the 5% areas intensity to the 95%, this is defined as the most energy content of the earthquake, and they define this as duration, significant duration. In this case, from 5 to 95% is obtained as 12.15 seconds. So these are two ways you can find the duration of an earthquake: a bracket duration and areas intensity. This is part of your mini project. When you pick that Seismosignal software, it's part of it. Once you give your input motion, it will provide you the areas intensity also. And from the areas intensity from the 5% to the 95%, I will ask you to find the duration, the significant duration. So for using both methods, you'll find it. Just to give you typical earthquake duration for epicentral distance less than 10 kilometers, for a magnitude of 5 on the Richter scale, a rock site can have 4-second duration. A soil site can have 8 seconds. This is just general to give you a feel of what the duration look like. A magnitude of 6.5, you can have a rock site 11 seconds and a soil site 20 seconds. Now, the big observation is this: a rock site of 4-second duration for the same earthquake than a soil site of 8 seconds. So it's having longer duration in soil sites. When we say soil site, You have the ground, and you may have, let's say, this kind of stratification. Let's say this is bedrock. This is soil. So you may have a recording station here. You may have another recording station here. This is on rock. This is on soil. That's what we mean by on soil, because it's getting amplified on soil. Soil is more flexible. So it takes more time to pass through. That's why you have it in soils. In soils, all of them have larger duration and smaller duration in rock. In US, especially the eastern part of US is a soil rock site. This is the eastern part of US. Or what we mean by is the soil is much shallower. The bedrock maybe here, the soil is very shallow. Let's say in this case, it can be, let's say 50-meter soil. But the western part, like California, it's a soil site. It's a deeper soil. I don't know exactly the average depth, but assume for now, let's say maybe 200 meters or 300, more than that. So earthquakes, when they occur in California, they get more duration than in the Western US. So that's the takeaway from here. Prediction of motion for design purpose. What it means is, we have recording stations all over the world, but still we miss significant points. Let's say you have a recording station here, and you can design your structure with this input motion. But there are so many other sites. Let's say we are building a dam here. We don't have a recording station here. So how we predict the earthquake here for this site? Even if you have a recording station, it doesn't mean you have to wait for the earthquake. You can have some records in the past, you can use it, but you don't know how much is coming in the future. Maybe larger earthquake can happen. So you're not going to use directly what you have. So this process of predicting earthquakes or input motion for a specific site, that's what we call predicting ground motion. And there are two methods nowadays: the PSHA, probabilistic seismic hazard analysis, and DSHA, which has been used in the past, which is called deterministic site hazard analysis. We usually don't get involved in this as a geotechnical or a structural engineer. It's more like geologists and seismologists do that, because this involves a lot from the point the earthquake occurs, how it travels, and to coming to the site. What it does is you identify your fault area. So it's all the process starting from the focus point to our site. So the way we predict is for critical structures. You identify, for example, if it's a nuclear power plant, you identify all the fault or the source zones within 300 kilometer or 300-mile radius. Once you identify all fault zones, then you characterize them. What kind of fault we have, how active they are. Do we have previous records from these faults? We collect all the data. So these are the steps: 1A, 2, 1B, earthquake sources, identification, which means identifying the faults, the location, geometry, and everything. Then earthquake source characterization, occurrence frequency, slip rate, maximum magnitude in history. So all seismologists, geologists, they do that. From the point they study everything, and they produce GMP, ground motion prediction equation, which is attenuation relationship. Okay, if it occurred here, my site is right here, then there is damping when it passed through. There is called attenuation relationships. What they are trying to do is the maximum acceleration reaching to the bedrock near to our site. So there are GMP relationship, attenuation relationship. They apply all that. They do hazard calculation, return period, and the PSHA, DSHA we discussed. And finally, they give us the acceleration response spectrum right here, ground motion response spectrum they produce right here. Then our task starts from here. We use the input from the bedrock, and we do site amplification through the soil. That's a geotechnical engineers. We do site amplification with or without the soil. This is what it is called SSI. Once you get the input motion at the bedrock, you do SSI, soil structure interaction. You analyze it with a free field without the structure or with the structure. And you can take the motion from bedrock to the foundation of the building. Then assume some springs, then pass it to the structure and see the behavior of the structure. So I have been using a software called SASE to do all this. We model this entire thing and run the whole thing together. The top part is finite element, but the bottom part for soil is wave propagation. The wave propagation we studied in chapter 3, that comes into play here. This is where you need the cutoff frequency, the motion parameters, and everything. So anything up to the bedrock, we get help from our good friends, geologists, geophysicists, seismologists, and even you may get a chance to work in this area. But as a geotechnical engineer, as a structural engineer, most of our task is we receive the input motion here, and we do the analysis with the site amplification and SSI with the structure. But the prediction here, it's usually done, and you don't use directly what you get from recording stations. On that prediction, you know, we call it site-specific. You know, depending on what site you are, we are doing a site-specific study. But this study is also prepared by some code books. If you are doing a general structure design for, you know, residential buildings, you have some values. For example, the US code ASC 716, American Society of Civil Engineers, there is a code book, a reference guide that we use. It provides the peak acceleration values for different regions of the US. You see it's much larger acceleration in California area and much lower acceleration in the Minnesota, or where I am. I'm in the Michigan area right here. So for various regions of the US, those books, they provide acceleration coefficients and a guide how to develop the response spectrum, depending on the soil type and everything. So in some cases, this, for example, for critical structures such as nuclear power plant or a critical dam, you're not allowed to use this. You have to develop your own site-specific. It's very time-taking, and this is what we discussed previously. The site-specific is you're not allowed to use the code books. You have to develop it your own by considering all the sources. For example, nuclear power plant case, I told you, we cover 300 miles. That's about, I think, 700 or 600 kilometer radius. Within that radius, we identify all the source zones, the data, and do the attenuation. And that it takes years to do that. Then finally, once the input is ready here, then we do the actual SSI. So this code, whatever you read from code books, is for common design. For residential buildings, it can be also commercial, but not critical structures. If it's critical structure, you will have to develop your site-specific. So let's say, you know, the prediction is happened, so we have input motions at the local site. This is our interest as a geotechnical structure engineer. This is where we are. We usually have the input motion available at the bedrock, even sometimes at the ground surface. So we don't care much about, you know, how the earthquake comes and what's the value, everything. The geologists, the seismologists, geophysicists, they do that for us, thanks to them. But once you have it here, now it's the civil engineers, geotechnical engineers, and the structural engineers apply this input motion, do soil site amplification or SSI with the structure. There are different softwares to do this. For example, SAP and StarPro, they model only the top part. Or FLAC can model also the soil, but it has limitation. You cannot model much. There is an advanced software like SASE. It can model much large area of the soil together with the structure. So ground motion recovery is usually at bedrock level, and the process input motion is at the bedrock level too. Okay. So you have ground motion time history right here. You process that motion, remove some noise, or it can be a rock site. This is a rock site where the building is on rock, or the rock is in shallow depths. And so soil site, you have the building sitting on soil. For a structure sitting on soil structure interaction analysis or site response analysis needs to be performed to include soil impact. So for this, if there is soil underneath, you need to include the impact of the soil. So that we need SSI. If there is no soil, like a structure on this, you can assume rigid base. And do StarPro or SAP 2000, it can do this. But if you have the soil, then the flexibility of the soil, sometimes commonly what they do is you can try to include, a SAP model with a spring. The springs are to account for the presence of the soil. But there is a significant limitation in the springs too. So we end up with SSI. You include the soil entirely and with the structure. FLAC has a capability to do that but it's not practical. It's not for design purpose because it has a limitation how much soil it can include. Because of the fine mesh required, the finite differences here, they will be too large in number, and the solution is very time-taking. But commonly for nuclear power plant, we use a software called SASE. You may not know it. It's very specific to nuclear power plant and advanced structures. So if it's a rigid, for example, for nuclear power plants, if it's a rock site, we're allowed to do a fixed base analysis, but the shear wave velocity or wave velocity in rock, it should be more than this, 5,000 foot per second. If it's a soft rock, which means a velocity less than this, we're not allowed by US NRC. NRC is the Nuclear Regulatory Commission, which governs us for in the nuclear industry. So that completes this chapter. Main reference for this chapter is reference 1, SL Kramer book, chapter 3. But many of the resources are from online. And you have a mini project here, which has a weight of 10% weight. You'll get raw data acceleration from some of the websites. USGS can give you that. And pick another quick with a magnitude larger than 7. And perform the following tasks using freely available programs. I recommend the Sesmo Signal program. You can try download there. From there, they give you free for 1 month. Go to that website, try to do it. If you cannot do it, if it's not downloadable, let me know. Send me a Telegram message and I can download and send you. That's what happened last year. They tried. Probably they had difficulty to download it, and I had to download and send them. So try it first. If you cannot do it, let me know. So get that software and do these activities. For raw acceleration, just do plot acceleration time history, and then integrate for velocity and displacement and plot them, and see how the plot looks like. Is it drifting? If it's drifting, do a baseline correction. So they have a clear manual. You can read, how to do tasks. It's a small software. It's not that complicated. And find the PGA, peak ground acceleration, peak ground velocity, and peak ground displacement. Once you have the acceleration, velocity, and displacement plots, just pick the peak values. And find the duration of the earthquake using both methods, bracketed and area intensity methods. And get a response spectrum plot of the acceleration time history. Do all this, you'll master the chapter if you do this. And the response spectrum plot, that's what mostly we use for design. Okay, that completes the chapter, and it's right on time. I have a meeting right now, and if anybody has any question, you can send me email, or you can put it in Telegram, and we'll communicate from there.